9-3 alpha lesson. So here's a question from the end. Which of the following gives a Taylor polynomial of order 5 approximation of sine of 1.5? So do you understand what's being asked? They're saying, instead of typing the sine of 1.5 radians in your calculator and getting an answer, how could you use the approximation, the Taylor series approximation, to get this? And they're telling you to go to order 5. Order 5 means you have to go to the 5th degree term. Yes? Well, the sine's an odd function, so that's as far as you're going to have to go. If they said order 6, it would still be the 5th degree function, because that exponent of 6 is going to give you a 0, because the sine's an odd function. Okay? So that's what's being asked. That's at the end of the section, and we'll come back to that, but that's not really as much as what we're going to focus on for the beta lesson. So we've got this. We've got polynomial functions and power functions. So a power function, ready? The independent variable is the base. And you have a polynomial function which has multiple power functions in it, as opposed to an exponential function. The power series, you can have Taylor or Maclaurin. And ready, Maclaurin is a subset of Taylor because Maclaurin is just centered at 0, which is the most user-friendly way to get your mind around it. And then you move on to Taylor, where you just do the slide. Geometric series. Well, what's a geometric series? Well, that's exponential as opposed to power function. And if it's geometric, you keep multiplying by the same constant ratio. So the independent variable is the exponent. And transcendental is like all else. Transcendental are functions that can't be written as polynomials, like sine and cosine. They can be approximated by power series. And here's what here's the connection you're trying to make. This is linearization, which we did in chapter 4. And linearization means that you find the tangent line to the function. And then if your delta x is small, and you use the value on the tangent line to approximate the value of the function, then you're going to be close. And you can tell what's happening. Because if the function's concave up, then you're going to under-approximate the value of the curve. If it's concave down, you're going to overestimate it. But how is that related to what you're doing here? Well, this is what you're doing. The y-intercept is f sub 0 over 0 factorial x caret 0. That's your intercept. The slope is the value of the derivative times x over 1 factorial. So a Maclaurin series of order 1 would be the linearization. And then what are you doing with it? You're going past order 1 to the second derivative and the third derivative and the fourth derivative. But what you did earlier, which wasn't really that difficult, I hope, in chapter 4, with linearization, it just represents the first two terms of a Maclaurin series. And it's that connection that helps you understand this. Oh, I did that in chapter 4. That's yesterday's news. That's not going to help. You have to scaffold this. That's what this is. If you can connect it, it's going to make it much easier for you to succeed with this. So here's example 2. So example 2 says this. The interval of convergence is -1 to 1. And we have this function. 1 divided by 1 take away x squared. And we're going to do this to order 6. So the first term is a 1, which we wrote as x times 0. The constant multiplier is x squared. So you'd have 1 times x squared. X squared times itself is x to the 4th, times x squared gives you x to the 6th. That is the 6th order series. Okay? Where the first term, g sub 0, it's geometric, is 1, and the constant multiplier is r squared. So how much are we off by? We're off by everything that would be added to the 6th term. Yes? The logical? It's 100% logical. Except what? That's an infinite number of terms. We can find the sum of it. Why? Because it's geometric. It's an infinite geometric series. So the error would be x to the 8th, x to the 10th, all the way to the right without bound. Which is what? First term is x to the 8th over 1 take away the constant multiplier. So this is going to give you the error. X to the 8th over 1 take away x squared. Done. Because this thing added to that as far as you got would give you that. So I went to the calculator and I said, all right, what are they asking for in example 2? You want the error at 3/10. So the function, we put 3/10 in the function, and it gave us that output. Then we went to y2. What's y2? It's the 6th order Taylor series, Maclaurin series. So we put 3/10 in that. And they're not the same. They're not the same because we stopped at the 6th term. So what happens? This is your x. Your x is 3/10. So I put 3/10 in this truncation algorithm, which is the first term divided by 1 subtract the constant multiplier. And it gave you this very small number, which is the scientific notation. And then I said, add this number to y2 of 3/10. Well, y2 stopped at the 6th order. Add the error, and it gets you back to the exact answer.
Why was the first term x to the 8th?
Because you went to the 6th, you stopped at the 6th term. So everything you're off by begins at the next term after that. So when you use the constant multiplier x squared times where you left off, the first term of the error would be x to the 8th. You all good with this? So that's your model. You're going to problem number 13. So for 13, first off, the interval of convergence would be negative 1/2 to 1/2. Why? Because you have the first term divided by 1 subtracted constant multiplier. So 2x, your constant multiplier, has to be less than the absolute value of 1. Otherwise, the series isn't fault. The middle term of the H chart isn't going down. So you would have, you've got your H chart, and here's your sum. This is your sequence, and this is your series. So I've got 1, 2x, your term is 1, first term is 2x, second term is 4x squared. So the sum for 1 plus 2x, 1 plus 2x plus 4x squared. Well, these values, the only way this is converging is if your constant multiplier, the absolute value, that's less than 1. So when you drop the absolute value, that gives you 2x is between negative 1 and 1. You just divide it 2 across the compound inequality. The parentheses mean the endpoints are not included. Because this would not converge at 1/2 or negative 1/2. So then what? Well, they say go to the 6th order, which is 64x to the 6th. So what comes after that? Those terms. Your constant multiplier is 2x. So we'd have 2x to the 7th, which is the first term, divided by 1 subtracted constant multiplier. Except in this example, you need the absolute value symbols. Why? Because some of the exponents are odd. Like the interval is negative 1/2 to 1/2. If you put a negative value in here, you just want the truncation error. You want how much it's off by. Make sense? What is the error amount? We don't have directed distance for the error. So that's as far as we're going.